Well, hi there. It's great to be with you again because today we're going to have a look at the strange and mysterious yet amazing and rewarding world of ellipses. Ellipses are the most amazing little beasties. You're going to learn to love them. So, there's one, and he's smiling at you. Of course he is. So, let's turn the page and get into the wonderful world of the ellipse. Who needs TV when you've got ellipses to look at? That's what I think, anyway. Yes, I know what you're thinking, just don't say it. All right, introducing the ellipse. Well, firstly, we're going to look at a circle because I'm going to reveal to you an amazing fact about circles. I won't spoil the suspense. Here is the equation of a circle. Okay, it's x minus h all squared plus y minus k all squared equals r squared. It's a generalised equation where h and k are the coordinates, x and y coordinates of the centre, and r is the radius, right? Now, watch this. We're going to divide both sides by r squared and get a new form of the equation. And here it comes. Now, the reason I did that is because something very amazing is going to happen, and you're going to realise that a circle is really not a circle. Well, kind of isn't, because, yeah, that's a circle. Now, here's the equation of an ellipse, right? Watch this. Watch this. Look at that. Now, does that look similar to the equation above in the blue box? Certainly does, except that I've called the denominator on the terms to the left of the equal sign a squared and b squared instead of r squared. Okay, that is an ellipse, guys, and it's got the same centre as the one in the blue box above, and it's got an x semi-axis. What's that? Don't worry, I'll tell you. Of a and a y semi-axis of b. Now, this is the deal. When you've got a circle, the a and the b terms are the same and become the radius. When it's an ellipse, they are different. They are different. So, that's what you get. A circle is simply just an ellipse where the a and the b are the same. And the x semi-axis is just that half the distance. It's kind of like the equivalent of the radius for in the horizontal direction for when you get a circle, and the b semi-axis, the y semi-axis, which is equal to b, is basically just that distance from the centre to the top vertically in the y direction. That's what it is. So aren't you surprised? A circle is basically just a special case of an ellipse. Wow, I reckon that's pretty cool. So, therefore, if A equals B, you get a circle. So there you go. Yes, a circle is just a special kind of ellipse. I think that's fantastic, because I learned circles well before I learned ellipses, and of course it makes perfect sense when you think about it, doesn't it? It does. Alright, so here comes the geometry of an ellipse, okay? I need to explain a few things to you. Now, okay, we've got a situation here where we're supposed to find the equation of the locus of points P satisfying PA plus PB equals 8, where A is the point with coordinates -2 and 0, and B is the point with coordinates 2 and 0, all right? Now, I'm going to actually just, hey presto, and oh, there it is. But I'm going to explain to you what it's all about so that you'll really get this, okay? The geometry of an ellipse is absolutely amazing. I want you to imagine that those points 2 and 0 and -2 and 0, A and B, are what's called the foci, the focal points of the ellipse. And I want you to imagine that that diagram is actually a pin board, and we're going to put some drawing pins, some thumbtacks into the point A and B. Now, and we're going to attach string to those points A and B, and we're going to pull that string. That string is exactly 8 units long. Look at the equation, look at the geometrical thingy above, PA plus PB equals 8. Well, that's how long the string is. It's 8, right? And we're going to, once that both of those ends of the string, one's attached to a thumbtack and one's attached to B thumbtack, we pull the string as hard as we can with a pencil or something that's got a writing tip on it, and then we move that pen wherever we can. There is where the pen goes, and there is the string. That is the string, right? From A to P and back to B is the string. And we're moving it. The pencil is at point P, and we're moving that pencil wherever it'll go, and that is the shape that it traces out. That is the shape. It would also be, it could be there, it could also be there, okay? Do you see what I'm saying? It's so exciting. And this is there's another point that it could also be at, because in all those instances, the combined distance from A to P and then back again to B would be 8 units. That is the significance of the geometry statement of how you get an ellipse, okay? It's even more exciting than this. I could go on and on and on. Of course, I won't. But there is I've got to tell you about this. There's a wonderful chamber in St Paul's Cathedral in London, and it's called the Whispering Chamber. And it is an oval-shaped room. It has an oval shape. The walls are in the shape of an oval if you're looking down from above. And there is a focal point A in the room and a focal point B in the room. And such that if you even whisper, it's quite a big room, so if you whisper from point A, no one would ever hear you at point B. But because you're whispering from the focal point of this ellipse room, what happens is the sound bounces off the wall to any point, and because of the geometry of an ellipse and the shape of the angle with which the sound waves hit the wall, they always bounce back and always go exactly backwards through the other focal point. Always. So they're concentrated and sent back through the other focal point, so that if you stand at the other focal point and someone whispers to you from point A, or vice versa, you will hear exactly what they're whispering without any distortion. That is awesome. And I don't usually use that word lightly. That is awesome. So there you go. Sir Christopher Wren, who designed that cathedral, knows all about that, or did know all about that. Now, when you get an ellipse, that is the general statement. P to A plus P to B equals whatever number you'd like to have, but you have to make sure that, yeah, that's 4 units long in that instance. See, that A to B is 4 units long, and the combined distance from P to A plus B to B is 8 units. Now, there's one little thing here, that the length of the string, as it were, has to be longer than the distance between A and B. Otherwise, well, it's a nonsense. It wouldn't work, would it? Because you haven't got any slack in the string at all to pull tight on with your drawing instrument. So if PA plus PB equals, I'll call it little a, and the distance from A to B is less than A, then you've got an ellipse. Now that's what I was just saying. So just digest that. The length of the string is A, the distance little a, the distance from capital A to capital B is less than little a, yes, you've got an ellipse, okay? Now, as A goes down, say 7 or 6 or whatever, as little a goes down, but the distance from capital A to capital B, the foci, is still less than that, it still works as an ellipse, but you can imagine, if little a is getting less, then the string is getting less long, okay? And therefore the ellipse shrinks. Isn't this great? It shrinks, and it shrinks horizontally, inwards, and vertically around the focal points A and B. Now I'm going to show you this on the next screen. There is the original one that I just did on the previous screen, and we're just putting in a little bit of all the information onto it. Now, there we go. Now, there, I've drawn it symmetrically in this case. Okay, I've drawn the string symmetrically going to the y-axis so that each branch of that string is exactly 4 units long. Now, that is my original one that we just did on the previous screen. That's the actual equation of it, in case you're interested, but we haven't got into that yet. And that's my geometrical statement, right? That's the one we're working on here, okay? Now, hey presto, oh yes, I'm just showing you that the 4, I just put a purple ring around, is the same as the x semi-axis, and the root 12 that I've just circled is the same as the y semi-axis. Okay, so the 4 is A, the root 12 is B. Yippee, fills us with glee. Now this one I've just, hey prestoed on you there, is a shrunken one. Okay, so therefore I'm using the same foci, A and B, but I'm saying that PA plus PB equals 6. Okay, the length of my string is only 6 units long. Same foci, but shorter piece of string. Yeah, there you go. You see that? Now, this equation, I think I've even worked that out for you. Yes, but we're not worrying about that equation yet. We'll come to that later. I just want to show you the geometry of the whole thing, the way it works, yeah? All right, more excitement coming. There's the next one. Now, I've drawn all 3 of them concentrically now. Well, the third one, the red one, you can see the inner one on that diagram I've just showed to you, is basically PA plus B, well there's PA plus PB equals 8, the original one. There's PA plus PB equals 6, the one on the top right. And here's the next one, PA plus PB equals 5, okay? It equals 5, all right? That's that one. You see how your ellipse is shrinking? It makes sense, doesn't it? Now that 4th diagram that just mysteriously appeared is what happens. Now let me ask you this. The distance between A and B is 4 units, isn't it? So what would happen if I said PA plus PB equaled 4? Good heavens, what would that mean? Think about that. Well, ladies and gentlemen, it means that my string is exactly the same length as it is from A to B. So there's no slack in the string at all. There it is, okay? For that purple line from A to B is my equation. That's PA plus PB equals 4, and it's simply a straight line joining A to B, okay? That's it. Now, if PA plus BB is less than 4 in this case, or little a, look, forget it. It's impossible. No locus would exist. Does that make sense? Yeah, it makes perfect sense. It's so exciting, isn't it? Now, that was a lot of information that I gave you there. But if you use that thumbtack and length of string model, you will really understand this stuff. And you will recognise the geometrical statement PA plus PB equals something as whether it's an ellipse or whatever it is. You will know, okay? Right, now we're going to launch into the algebra mode. Now, I need you to fasten your seatbelt and take a big chill pill because this is Algebra City. Now, we have to find, this is the same equation, but we have to do it with just the algebra way now. Right. And then secondly, after that, we're going to do it with this amazingly refreshing and simple geometrical way. Okay, but this one has to come first. Right. Drawing our diagram. What do we got? Yeah, that's it. Same deal as we've had in the previous screens. Now, here comes my geometrical statement. PA plus PB equals 8. Yes, let's go now. We have to do the algebra. Right. Now, there's PA. See if you agree. Yes, I do agree. P to A is x minus negative 2, all squared, plus y minus 0, all squared, square root of the whole thing. P to B is the square root of x minus 2, all squared, plus y, all squared, and that comes to 8. Now, here's the first big problem with trying to solve this. Look what a mess it is. If I basically try to square that left-hand side as it is, look, I'm going to get all of the first square root squared, plus 2 times the first square root times the second square root, plus the second square root all squared. Because remember, it's not just the first square root all squared plus the second square root all squared. That's wrong. Remember, what's a plus b in brackets all squared? It's a squared plus 2ab plus b squared, not just a squared plus b squared. So in order for us to survive, this is very essential, you have to take one of those square root sides over to the right-hand side where it becomes manageable. Okay? And it doesn't matter which one you take, you just have to take one of them. Okay, here we go. Now, I think I took the second one. Yeah, I left the first one there, took the second one over. Now we can square both sides on the right-hand side, and it's much more manageable because the two terms, one of which is only a number, so that makes it easier to do. Let's go. Ready? Square both sides. Right, here we go. Get ready, chill pill. What's all that? Okay, there's the first. Yeah, I can see what I've done. The first term there on the left of the equal sign is all that first square root thing squared. Then the right hand side, of course, is the first term squared, that's 8 squared is 64, plus 2 times the 8 times the negative square rooty thing, plus the square rooty thing all squared. Now there's a lot of messing around. We've got to expand those brackets out. I told you this was Algebra City. So come on, just go slowly. Don't freak out. It will be fine. But there's a lot of mental processing going on here, so just be very careful. Very, very careful. Great. Cancel time. The X's cancel. Great. The Y's cancel. Great. And I think something else. Yes, the 4's cancel. Well, that's great. Now, what do we get left over with? This beast. Okay, well, see, the bad news is, the good news is it's a lot simpler. But the bad news is we've got to square both sides again. I can hear you saying. However, look, we can make life a lot easier for ourselves if we just look for the common factor, which is 8. So do that. Thank you, Mr. Snail. How are you slithering today? Good, he says. Okay, come on, we're going to do this. We're going to divide by 8. Therefore, x minus 8 equals minus 2 times that. My goodness, that's infinitely easier, guys. I wouldn't like to square it like the way it was before we divided by the 8. Okay, you ready? Here we go again. Square both sides. Off we go. Right. Here we get this. X squared minus 16x plus 64 equals 4 times. Remember, you've got to square that minus 2 as well. The thing in the square root sign, right? Now, I think we can get rid of that 4 on the right-hand side outside the brackets now to make it easier. Good. Now we have to do some simplifying now. Oh, yes. Very nice. Excellent. And I think that's all. So now we have to just get everything over to the left-hand side so we can see what we're doing. And that looks right. Yes, it does look right. Excellent. Now, I think we have to... What have we got? Oh, no, we don't have to complete the square or anything. It's really... Oh, look, this is nice and simple. Look at this. I've multiplied through by minus 1, and I've taken that 48 over to the right-hand side. Now I'm going to divide by 48. It's going to be great. And look what happens now. I'm there. You can see, guys, I'm there. I've just got to cancel out those coefficient-y terms, and I've got my beautiful little ellipse. Yes, yes, and yes again. Mr. Box. That's very, very exciting. So it's an ellipse. It's got a centre of the origin, and it's got an x semi-axis of 4, and it's got a y semi-axis of root 12. And another... Oh, yes. Oh, I thought I did another box. I didn't. And I'm drawing it for you now. Come on, look. Here it is. Here it is. That's 4 units, and that gives me those intercepts. Of course, you have to work out the intercepts of these things if they ask you to draw the graph of it, which is a bit trying, particularly when they're not centered at the origin. But you can still do it, no problem. Just a bit of algebra here and there and everywhere. Here's the root 12 thingy from the y semi-axis. That's root 12 units long, and therefore there's my y-intercepts. Yes, ain't it grand? Good. What do we got now? Find the equation of... Oh, you wanted to have another closer look, did you? Oh, all right. Hang on. Wait a minute. There you are. There? Nice. Isn't it beautiful? Yes, all right. Now, come on. We've got to go. Now, what's this one? Find the equation of the locus of points P satisfying PA plus PB equals 8. Oh, it's the same one. I'm a silly sausage. And it's the geometrical approach. Now, watch this. This is going to just floor you. It's so easy. Watch. Now, there's the diagram I had before, right? There's the diagram I had. Now, just go with me. There's my foci. Right. Now, do you know... Oh, I've got to tell you this. I'm sorry. Focus is a Latin word which means fireplace, and it's thought that's got nothing to do with focus, except that it's thought that through the ages, when people shined magnifying glasses and used the focus of the sun's rays to create fire on a piece of paper, that might be where the word focus came into vogue for this kind of a focus, a focal point where things are concentrated. Isn't that fascinating? All right, I'm sorry, I'm getting carried away. Now, here's my geometrical approach. I'm going to do a symmetrical approach because it makes life so easy. There's P for you and me. Now watch this, guys. Watch this. I've got to show you this little proof here. You don't need to do this every time, but I'm about to show you that, see that PA plus PB equals 8? Well, I'm about to prove to you that the x semi-axis will always be half of that number. It'll be 4. Now, but here it comes. Let the distance between A and B equal 2f, f being for the focus. Okay, there it is. Let BC, now what's that? BC plus AD, I don't even drawn them in. Oh, there they are. BC, B being from the focus to the outside vertex, as they call it, and AD being the same thing. We'll call them X as shown, right? Now you can see that if P, that's the point on the ellipse, is at, if you swung it around, righto, anti-clockwise, if you swung that pencil drawing tool right around and got it over to C, you'd have both of those lengths of the string sitting horizontally, wouldn't you, right? You would. And you'd have the one from A going all the way to C, and you'd have the one from B going to C as well, but only from B, if you can get what I mean. If you think of it as a piece of string, you'll understand what I'm saying, right? So if P at X and Y is at C, then AC, A to C, that's the first branch of the string from A, plus C to B, that's the second bit of the string back to B again, would equal 8, wouldn't it? Of course it would. Therefore, what I'm saying is that's A to C is 2 F's plus an X, and plus the CB is another X. So therefore, simplifying that, we get 2F plus 2X equals 8, and therefore, ba-boom, ba-doomch, we get F plus X is 4. And F plus X, everybody, if you think about that, F plus X is the X semi-axis, right? So if 2F's and 2X's equal 8, which I've just shown you, then F plus X equals 4. So you just halve that number you see in the question statement above, the 8, halve it to get 4, you got the X semi-axis. Ain't that grand, right? But you don't have to prove that every time, but I wanted to prove it to you now so that you will know in the future what to do, right? Good. Yeah, that's half of 8. Goody, goody, goody. Now, here we go. Here's our ellipse. Look how easy it's going to be now. You watch this. You're going to be amazed. The first thing we can tell is that this ellipse has a centre at the origin because A and B are equidistant away from the origin. You just average the points A and B to get the centre point, right? Okay, that's what you do. So, now, the x semi-axis is 4, so we almost know about everything we need to know about this ellipse now, just from the statement of the question, okay? Right, now here I go. I'm putting it into an equation form now. Right, so look, you can see I've got everything in there except the b. How simple is this? And the b is very easy to work out. Very, very easy, because dear old Mr. Pythagoras has saved the day again. Look at that triangle I've got to the right hand side of the y-axis, formed by P to B, the y-axis, and the x-axis, right? Watch. Still need B, but it's easy. In the right angle triangle POB, right, you can see above, we know that PB, was that right? PB? PB equals 4, which is half the length of the string. We know that OB is 2, because that's the distance from the centre to the right-hand focus. So we can just apply Pythagoras' theorem, and my goodness, it just all falls out. And therefore we get that P to O is root 12. Well, there you go. Now we've got our equation, because that's B for you and me. Hence, there's the equation of my ellipse. Put a box around it now. You tell me, which was easier, the page of algebra on the previous screen, or this. I think I know which one I like, and they're both equally valid, okay? But you need to do the algebraic approach just for your own confidence, to know what to do, and it's just really good maths for you to do and to learn, to just put yourself in four-wheel drive mode and not to freak out when you get these complicated algebraic forays, you know, thingos to do. All right, that's that done. Now, all right, now this one here is we're doing some transformations now. This is pretty simple. We've got an equation of a circle, x squared plus y squared equals 1, so that's a unit circle, radius 1, centre origin, and we're going to transform it. In part A, we're going to dilate it by a factor of 4 from the x-axis, that means a y, in the y direction, if you think about that, followed by a dilation of a factor of 5 from the y-axis, and of course that is in the x direction. Now there's two ways to do these, and I'm going to show you both ways just in case you haven't got it from your methods work, okay? This is really just getting into methods now, maths methods, okay? Alright, if we had an original equation of that thing, we're dilating it by a factor of 4 from the x, and we're dilating it by a factor of 5 from the y. Right, now that's the two things we have to do to it. Here comes method 1. There's two methods I'm going to show you, right? There's the logical way, and then there's the quick cookbook way, which gets you the answer quicker, but doesn't have much intuitive understanding behind it. Here's the logical, intuitive, longer way. Right, there's x and y. We're going to... Right, now, step 1 dilates it by a factor of 4 from the x, which means it's going away from the x, which means it's going up, okay, to get away from the x-axis. Therefore, it becomes x and 4y, okay? Here comes step 2, dilation by a factor of 5 from the y. Yes, it goes in the x direction to get away from the y-axis, and it's by a factor of 5, so it becomes 5x and 4y. Now, that is our final point. So I call that x dash and y dash, don't I? Yes. So therefore, to summarise that, I've just summarised it all in a non-graphical form, like that. Okay. Now we've got it where we want it now, guys. Because look, x dashed is 5x. Look at the equivalence of those bracketed terms to the right-hand side of that little thing I just did in the line above. Yeah, and y dash is 4y. So that is what I call the key for you and me to work out my transformed shape. You just substitute that key into the original equation. That's what you do, and you get your new image, as they call it. Sub into the original equation, thank you, Mr. Snail, and to repeat, we've got x squared plus y squared equals 1. We've got x is x dashed over 5, and y is y dashed over 4, which we got from the key, but I've rearranged it because obviously I've got to plug into the x squared plus y squared equals 1 equation where you just have x's and y's, no x dashed and y dashed. Okay, so you sub what x is from the key into the x term of the equation, you sub from y from the key into the y term of the equation, and look what you get. Da-da-da-da, and there it is. There it is. There's my ellipse. Therefore, you then drop the dashes, and you just say the image is that thing, and there you've got it. Okay, it's very, very straightforward, totally logical, and that's method 1. Here comes method 2. Now, method 2 is just a cookbook technique, which is really fast. If you're good at it, by all means use it, okay? But if you're not, if you're getting confused, it's different. It's the procedure is different, and don't confuse the two. If you're going to get confused, just use method 1. Okay. Okay. Dilation, y dilation. That is, the first one was actually a dilation in the y direction, so it's a y dilation of a factor of 4. If you do that, you replace y by y over 4. Now that's where I got to. Okay. Now, so what do you get? You get x squared plus y over 4 squared equals 1. Now, the x dilation, the second dilation was a dilation in the x direction by a factor of 5, so that means you replace x by x over 5, and you get that. There it is, guys, and that's your, that is your image. Now that was a lot quicker, but there's not much logic behind it that I can see, but it just works and works fast. Okay. Alright, you choose which one you want to use, okay? But you've got method 1 there, the logical one, if you ever need to fall back on it. Okay, here's part B. Part B of this question. Now we're doing the same dilations as we did before, but we're going to do a couple of translations this time. Here comes method 1, right? Method 1. Right. I'm going to label them, okay? You just saw me label them up in the question on the top of the screen. Transformation 1, 2, 3, 4, just so it's easy for me to refer to them, okay? Okay, so the first one, x and y, for transformation 1, dilation of a factor of 4 from the x-axis means it's going up away from the x-axis, so the y is going to get times by 4. Now, transformation 2, dilation of factor of 5 from the y, that means it's going to go away from the y in the x direction, so that's going to become 5x 4y. Number 3, now watch this. A translation of 4 units in the positive x direction, that means you've got to add 4 to the x term. That's what I've done, right? Now the fourth one, we're going 3 units down. So therefore you take 3 units off the y term and there you get it. Now that means my x dashed, my final resting place is x dashed, which is 5x plus 4, and my y dashed is 4y minus 3. And that is the key for you and me and fills us with glee, so we can basically be free of all this confusion. Now we're going to substitute from that key back into the original equation x squared plus y squared equals 1. Yes, Mr. Snail, thank you. You do a great job. Now, here we go. From the key for you and me, that's what x and y made the subject of the key are. And we're going to plug them into our original expression, x squared plus y squared equals 1. And that is what we get. Whoopee-doo. And, yeah, the image is, I'm dropping the dashes now. That's what I get. Okay? There's the box time. So that's pretty good, eh? You like that? All right. I'm going to move right along now. Now we're going to do method 2. Method 2. Now that's the quick, I call it the quick and dirty, but very effective method. Okay, so, right. What are we doing? Transformation 1, that means y dilation in the y direction by a factor of 4. Therefore we replace y by y over 4. Okay? It's kind of like an opposites thing, this technique. You do kind of like the opposite of what you're sort of looking at. Right, so therefore you get that. Da-da-da-da. Now, that's where we got to. Now, if we're doing an x dilation of a factor of, that is in the x direction by a factor of 5, what do we do now? We replace x with x over 5, and that's what we get. Good. Now, we're going to do the third one now. This is, we're going 4 units to the right. So in this particular technique, you replace x by x minus 4. Minus 4. Okay? And that's what you get. And the last but not least, we're going 3 units down. So we replace the y term with y plus 3. And here we go. That's it. Now, I think I'm going to simplify that a little bit more. The image is da-da-da-da-da-da. There it is. It's pretty nice. It's absolutely marvellous, actually. There you go. Now, that's how you do the transformation ones, all right? Now, I think I've got one more. So, just one more. Don't worry, it'll be over soon. Now, this one here is the other geometrical way of detecting an ellipse. Ellipses are members of what's called the conics family, and they're all related. Ellipses, hyperbolae, parabolae, and circles are all related, and you can make those shapes by cutting in certain directions into a solid cone. It's absolutely amazing when you get into it. Now, but just for the one we're doing now, I'm drawing you a little bit of a diagram. We're saying here that the equation of the locus of points x, p, x, and y, which satisfy the property that the distance p of p to the point f which is 1 and 0, which I've showed you there, is half of the distance, PM, which is the perpendicular distance to the line with equation x equals minus 2. Let's do it. Right, there it is. Now let's draw our little loci thing. Yeah, so I'm saying the distance from P to F is half of the distance from P to M, where the coordinates of M would be. Now you think about that. They've got to be minus 2. Oh, no, they're not. Oh, wait a minute, that's minus 1. Oh, no. It is minus 2. Yeah, I just drew it wrongly on the dotted line. Sorry about that. I'll have to fix that up later. But just imagine that x equals minus 1 says x equals minus 2. Can you? Thanks. Now, all right. Now that's the deal. I've tried to draw it so it looks about right. Now, it's a property of conics that, now this is the situation. If PF equals PM, if it did, then you've got yourself a parabola, right? Secondly, if PF is less than PM, you've got yourself an ellipse. And thirdly, if PF is greater than PM, you've got yourself a hyperbola. Now in conics language, F is what's called the focus, and that line, that vertical line x equals minus 2, is called the directrix, which you don't have to worry about right now, but it's incredibly exciting stuff. So this is the one we're dealing with here, guys, because PF is less than PM. In fact, it's half of PM. So we're going to do it algebraically because I don't know how to do this one geometrically. Let's go. Okay, here comes the algebra. Ready? Good. There it goes. Is that right? Look at it. Yes, I think so. Yes, I'm happy. Now, Mr. Snail, thanks. Off we go. Now we're going to get into the algebra and we'll get a nice, lovely little ellipse. Hopefully. What did I do there? I squared both sides. Remember, I had to square that half coefficient on the right-hand side as well. You've got to square each thing, right? And I changed the x minus negative 2 into x plus 2, and then I squared it. Now we have to simplify, guys. Here we go, multiplying out all that stuff. Algebra soup. Be careful. I don't like that quarter on the right-hand side of the equals, so do you mind if I multiply both sides by 4? Makes my life a bit easier. Much better. Now it's time to simplify. I think the 4s are going to cancel out. Yes, I like all cancellings. Now, nothing else is though, is it? So let's get everything over one side of the equation and see what we've got. Well, there's an x squared and there's an x term. That means if I've got a middle term like that x term, I have to complete the square to get linear thingies squared, linear factors squared, yeah? Come on, we'll do that now. Now, okay, I took the 3 outside and I'll put those 2 x terms inside the bracket. Now, it's much easier to do now. Come on, what's half of 4? The 4x, the minus 4x term is 2. 2 squared is 4. Okay, you put the 4 in there and then minus it straight away so you're not changing the left-hand side of your equation. You can still put the equal sign, equals 0. Now, I'm going to get that inside that bracket, that 3 open bracket x squared minus 4x plus 4 minus 4, I've got to get the minus 4 out of there because I don't want it in there. Okay? Let's do that. Yeah. 3 times minus 4 is minus 12. That gets it out of there. You've got to remember to multiply it by 3 for heaven's sake. Don't make that mistake. Now, we're nearly there now, guys. We're very, very close to victory. Now, okay, one more line. Yes, I've shown that completed square in all its glory, and I've put the 12 over the other side. Now, all we've got to do is divide both sides by 12, and it's ours for the taking. Look, that's my ellipse. It's an ellipse. There it is, centre 2 and 0, and x semi-axis is 2, and y semi-axis is root 3. Yes, a very big, enormous box for us. Yes, Box City. So there you go. That's it. It was an ellipse, wasn't it? How exciting is it? And I just wanted to show you it. There it is. I did an equation of it on the calculator. There it is, okay? And there is my focus there. In fact, there are two focuses in this ellipse, but we don't actually get to use the other focus. But you can imagine it's going to be exactly, if that 1 and 0 is to the right 1 unit of the y-axis, then the other focus is going to be to the left 1 unit of the other vertex, yeah, the x vertex. There's x equals -2, that's our directrix. There you go, and there's my P for you and me, and I've drawn the whole thing for you. It's mighty, mighty cool. And it's also the fact that anywhere on that blue ellipse you will find that the distance from P to F will be twice the distance from P back to that vertical directrix line. And you are a star. You are a star, and you'll go far. So that's it. That was very long, a very long session, but I think it was worth it because this stuff is fairly difficult to understand at first glance, and you'll have this to look back on whenever you need it. Okay, well, thank you again. Thanks for watching. Have a great day. If you're not sure, just go back and look at it again. You'll be fine. Okay, we'll see you next time for hyperbole. My goodness, that'll be so exciting. Bye for now.